until this point in the course, we've been dealing with derivatives. So the derivative was giving us the slope of our curve. It was helping us find the slope of a tangent line. It was giving us some ideas about how the graph of a function behaved. So that is one major part of the study of calculus. But now we're going to shift gears to something that is completely opposite of what we've been doing. So instead of taking derivatives of functions, we're going to be doing the antiderivative. Now we also call this integration, but this idea of having an antiderivative means that we're going to try to find now the function that has a given derivative. So when we're talking about an antiderivative, we're trying to find the function whose derivative, f prime of x, equals that function. So we will think about our derivative rules and think about what function that could have come from. So for example, you see 3x squared. What function has a derivative equal to 3x squared? Well, x cubed. That would be our antiderivative. Because x cubed, if you were to take the derivative, you get that 3x squared. So you see that we're actually going backwards. You're given the derivative, okay, 3x squared is the derivative, and you want to find the original function. Now, one thing about the antiderivative is this x cubed is just an antiderivative. It is not the antiderivative, because there's an entire family of functions that actually have this antiderivative. An entire family of functions that have a derivative equal to 3x squared. So let's think about this one, this 4x to the 4, or x cubed, its antiderivative would be x to the 4th. However, couldn't it also be x to the 4th plus 1? What would that derivative be? Well, it would be 4x cubed, and then the derivative of 1 is 0. Or it could be x to the 4th minus 3, because x to the 4th minus 3, its derivative is also 4x cubed. So really, it could be any constant. And so that's what we're interested in here, is when we're doing an antiderivative, there could be a constant. And we want to recognize that this constant, we don't know it. And unless we have some initial information, we can't find it. There will be some times that we find it, but we have to know a little extra information first. So every one of these antiderivatives needs to have this plus c, so that we recognize that any constant would also have this particular function, for this case 4x cubed, as its derivative. So always put a plus c. Now when we talk about finding the antiderivative, sometimes you hear the word antidifferentiation, but typically we call this integration. So the verb that we're doing here, we are integrating or we are doing integration. And this is the major rule here for integration. If you are integrating a derivative, you are finding its original function, but there could be a constant. We really don't know. There's no way of knowing that. So we'll always put a plus c for that. So what are a few of these basic integration rules? Well, the antiderivative of 0 would just be c, because the derivative of c gives you 0. So any constant would have a derivative of 0. Now, if you had just some constant like k, it could be 3, 5, 17, whatever, some constant, this will go to kx plus c, because what's the derivative of kx? It's just k. And then for any other function, if we're trying to find the antiderivative, it will be k times that function f of x plus c. So if there's a constant in front, it's just going to tag along. It's just going to stay in front of the function. You don't have to do anything with it except keep it around. Now, if you are adding two functions inside an antiderivative, then you will have the sum of those two original functions and then just a plus c. each of those functions get a plus c, but when you have a plus c1, a plus c2, we just generically call it plus c at the end. And then here is our major rule for finding the antiderivative. If you have a function to a power, this is the basic one, what's going to happen is, let's think backwards for how we find a derivative. When we're finding the derivative of a function, we bring down the exponent and subtract by 1, right? Well, let's do that opposite. We will add 1 to the exponent and we will divide by the exponent. So this is just the opposite of doing the derivative. But instead of subtracting 1 from the exponent, we now need to add 1 and then divide by that new exponent. So this rule right here, this is our major one that we will be using for a lot of what we do this semester. Second semester calculus looks at lots of additional types of integration. We're going to keep it relatively simple here in this first unit. It'll still be challenging, but we'll basically be doing just basic integration rules to get you used to it and to get you thinking in this terms of integration. Let's show a few examples. When you are doing these, you always need to get them into one of those forms. So 3x is in that form kx, or k times the function. And so what we're doing here is we'll just bring the 3 along with us, and then this is x to the 1. So our power rule here is we add 1 to the exponent and divide by the new power. I typically will write this as 3x squared, or sorry, 3 halves x squared. I'll typically bring the fractions in front, but that's going to give us our answer. And you can always check, take the derivative. What happens when you take the derivative here? You bring down the 2, leaving you with 3x, which is what we started with. For this next one, it's not in the correct form. So we need to rewrite this just like we did with derivatives as x to the negative 2. And so we'll use that power rule. We will add 1 to that exponent. So negative 2 plus 1 is negative 1. Divide by that new exponent and add c. Typically, you would rewrite these so that they just look a little neater. The x to the negative 1 you can write in the denominator, and that negative 1 we can just make this negative 1 over x and then plus c. Fractions, we'll handle them like we did derivatives. We will rewrite these. Sorry, square roots is what I meant. Square root functions, we will handle these like we did with the derivative. We rewrite these with irrational exponents. And so we have this t to the 1/2 dt. I do want to make a note real quick that this symbol in front and this dt always have to surround the function that you're integrating. This is our way of saying, hey, we're taking the integral and it's with respect to whichever variable that we need. So notice on number 1, we had the integral sign and then it was dx to tell us it was with respect to x. But on number 3, we had the integral dt because it was with respect to the variable t. So you always need to have that surrounding your function. It's the notation that tells us what we're supposed to be doing. If you leave that off, you really have not written it in the correct way. So now that we have this rewritten, we will do our rule. So we'll add 1 to our exponent, which takes us to 3 halves. We divide by our new exponent. And now we will rewrite these. When you're dividing by fractions, it's the same thing as multiplying by the reciprocal. So that becomes 2/3, and we have t to the 3 halves plus c. So, I don't do a lot of simplifying, but with these, I think it is important here for us to rewrite these because it's just dealing with a couple of numbers. It's not like we're factoring or doing anything crazy. It's just a little bit of simplification because if we were trying to take the derivative here, it would be easier for us to see. So I do want you to simplify these, but only to get the numbers cleaned up. All right, what about this next one, number 4? Well, really, this is the sum of 2 functions. And so we'll look at these each by themselves. What's the antiderivative of y? Well, that's y to the 1. So we'll do y to the 2 over 2. And then 2, remember that's just our k rule. And so you do 2 times whatever the variable is, which in this case is y, and then a plus c at the end. I would like to have this rewritten as 1/2 y squared plus 2y plus c. I just like to have the fraction in front of the problem. For number 5, what we're trying to do here is do the antiderivative of 3 functions. We have the 2 theta squared minus 3 theta plus 1. This one is with respect to theta, so we have our integral symbol and then the d theta to tell us this is with respect to theta. And we'll just apply our rule. We have a constant, so we bring that with us. And then we go to one higher exponent, divide by that new exponent. For 3 theta, we bring that -3 with us, and we add 1 to the exponent, divide by the new exponent. And then 1, that's a constant, but we need to include a theta with that. That's our k rule. And then a plus c. And then I would like to rewrite these fractions in front for everything, and we don't need a 1 in front of our theta, so we can just write theta. Now, what about number 6? I see a quotient here, and we had a quotient rule for derivatives, and we will eventually have something like a quotient rule for antiderivatives, but we don't have it yet. So for this part of this course, we'll always be able to simplify into some version of our power rule. So here, what we can do is we can make this x over the square root of x plus 1 over the square root of x, and all of that is with respect to x. And so what's happening on this one is we can simplify with our exponent rules. The first term is x to the 1 over x to the 1/2, so we subtract and we get x to the 1/2. And then this next one, 1 over x to the 1/2, becomes x to the -1/2. We put that in parentheses so that we know all of that is the function within the antiderivative. And now we do our rule. So we add 1, we get 3/2, divide by 3/2. Add 1, we get 1/2, divide by 1/2, and then do a plus c. For these fractions, since they are a fraction under the fraction bar, we do the reciprocal when we bring them up. And there we go. Now remember, you can always check these by taking the derivative. And as long as you get the original problem, you know that you've done them correctly.